Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be doing another example involving convolution, but in this case we map it over to what we call, let's just say, a multiplication type domain using eigenvalues and eigenfunctions. And essentially, in order to really grasp what is going on in this video, I would encourage the viewer to watch two of my previous videos. Specifically, the first one is called Eigenfunctions and Eigenvalues Clearly Explained, and the second one is called Eigenfunctions of a Continuous Time LTI System Clearly Explained. Additionally, this example builds off of another example that I did previous to this called Convolution Example Part 1, where this video is Part 2, and I will link all these videos in the top right hand side corner of this video. Now, in this example, we're tasked with finding an output y of t, given an input x of t equated to cosine 3t, where my system that the input goes into is this capital H, which is the integral from negative infinity to t of my input x tau d tau. And in this multiplication domain, we talked about how the output y of t of any continuous time LTI system is this eigenfunction, which is a complex exponential, times we called this the transfer function of my system. And essentially, as a recap, engineers would rather do this multiplication computation rather than do this input convolved with my impulse response h of t. Okay, similar to my previous examples, I do encourage the viewers to pause the video, see if they can answer the question, and then come back to the video and see if they received the correct answer. Okay, so now let's go ahead and solve for this y of t given x of t is equals to cosine 3t. And the first thing we have to do is find out this h of Sn, where in this case n exists all natural numbers. So for example, 1, 2, 3, and so on and so forth. And so we know that our transfer function h of s, I'm going to omit the n for now, is equated to this integral from negative infinity to infinity of my impulse response h tau e to the minus s tau d tau. From part 1 of this example, we found out that the impulse response h tau is equated to the integral from negative infinity to infinity u tau, or the unit step function, e to the minus s tau d tau. So again, we can go ahead and equate this to the integral from 0 to infinity e to the minus s tau d tau, where this unit step function goes away and our limits are from 0 to infinity. I hope this makes sense. So let's go ahead and take the integral of e to the negative s tau. We get 1 over minus s e to the minus s tau, and the limits are from 0 to infinity. So this becomes 1 over minus s e to the minus s times infinity minus 1 over minus s e to the s times 0. E to the minus infinity here all goes to 0, and e to the 0 here goes to 1. This becomes a plus plus. As a result, our transfer function h of s is equated to 1 over s. Okay, so now what I want to do is I want to draw a graph that depicts where we're going to with this solution. And to explain this graph, I'm going to say that this here is some complex exponential x n t, where we talked about how any signal, or most signals that we care about in engineering, call this x of t, can be decomposed into these complex exponentials added up. So we can decompose any signal x of t into many different signals. So we have x1 of t, x2 of t, all the way to xn of t. Right? Essentially, where for this situation here, to be completely explicit, this would be a1 e to the s1t, and then we add this to a2 e to the s2t, and this here is some an e to the snt, where again, the reason why this is the case is because we proved that this function here is an eigenfunction of an LTI system. So to continue with our graph, we then said that we can push each of these eigenfunctions into our system. So our system here is h of s1. Our system over here is h of s2. And our last system here, dot, 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 is h of sn. And what we're going to do is we're going to go ahead and add these all up. And essentially, we're going to say then that y of t is equated to h of s1 x1 of t plus h of s2 x2 of t plus dot, dot, dot plus h sn x and t. So just as a recap into some specifics and some observations I want to draw in terms of this graph that is very, very important in terms of engineering, especially for electrical engineering, where if we're given this random input x of t, where in this case it's cosine 3t, we can decompose that into the addition of these complex exponential functions, right? Where we say that these are my eigenfunctions of an LTI system, where we go ahead and multiply it by this transfer function at a specific complex frequency or complex variable, S1 here. For this one, it's S2, and for this one, it's Sn. Where finally, we get this output y of t, which is the addition of this x1 of t, which is my eigenfunction again, times this transfer function or this eigenvalue for each of my n existing in the natural numbers. I hope this concept makes sense, and I hope it kind of bridges the gap into why we studied eigenfunctions and eigenvalues in order to ease the work when it comes to doing multiplication and addition versus convolution. Specifically, in solving for y of t here, we are doing multiplication and addition versus if we solve for y of t is equated to xt convolved with h of t. This is a more complex problem to solve. And we need to also remember that although we're dealing with a unit step function as my impulse response, it could be something way more complex like a fourth order differential equation, where taking the convolution of that will be more complex. We would rather do this method instead. I hope this makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, to conclude the video, we can say then that h of s we found to be 1 over s, or my transfer function is 1 over s. We also said that we want to decompose this x of t into an x1 of t plus an x2 of t plus an xn of t. So in order to find this, where we decompose x of t into these complex exponential, we can do two things. The first thing you can do is use what's called the inverse Euler's identity for a cosine function. So we can say that x of t is equated to e to the 3jt plus e to the minus 3jt over 2. To be explicit, this is 1/2 e to the 3jt plus 1/2 e to the minus 3jt. As you can see here, this is x1 of t, and this here is x2 of t. Now what happens if my input doesn't decompose nicely into these complex exponentials? What we then use is a second method, which I encourage the viewers to actually do on their own. It's called the Fourier series, or the continuous time Fourier transform. And I've done videos on these two concepts. The first one for this Fourier series is called the Fourier series complex form or real form, clearly explained, part 1 and part 2. And I've also done a video on the CTFT, and that video is called continuous time Fourier transform, clearly explained. I'll go ahead and post those two videos in the top right hand side corner of this video. Okay, so now what we can do is we can see that our S here and here are our complex frequencies, S1 is equated to 3j and S2 is equated to minus 3j. So now I can go ahead and solve for h of S1, and I can say that this is h of 3j, which is equated to 1 over 3j. And I can say then that h of S2 is equated to h of minus 3j, which is equated to 1 over minus 3j. So finally, we can say that y of t, which is equated to h of S1, x1 of t, plus h of S2, x2 of t, is equated to 1 over 3j times 1/2 e to the 3jt plus 1 over minus 3j times 1/2 e to the minus 3jt. What I'm going to do here is I'm going to say that this is 1 over 3 times e to the 3jt minus e to the minus 3jt over 2j. And we know that, again, using Euler's identity, this here is equated to sine 3t. So we get 1 over 3 times sine of 3t. And if you checked out part 1 of this example, this is the same solution we received. Now, in this video, I tried to explain everything explicitly, but in a regular solution, especially given a higher order differential equation as my system, the summations given from my output tends to be easier to do than doing the convolution of the impulse response convolved with the input. I hope this video makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up, and please share the video with your colleagues and friends so they can also obtain the knowledge. And lastly, if you like what the YouTube channel is providing, please consider subscribing to the channel. It really helps the algorithm. Thank you.